Okay, so we have been describing the Laplace equation and a technique to solve the Laplace equation, namely the method of separation of variables using two independent variables and using rectangular coordinates. So in this lecture we will look at two important kind of boundary conditions. So we have this general method and solution also from within this method, and we will see how to apply it to specific boundary conditions, taking the two sort of standard boundary conditions which are of importance in the problems of this kind. So these are called Dirichlet and Neumann boundary conditions. Okay, so the Laplace equation is del squared u equal to 0. So we have dou squared u by dou x squared plus dou squared u by dou y squared equal to 0 in Cartesian coordinates and with two variables. So we have seen how to write this u of x comma y as some x of x times y of y, and then work out the ODEs connected to capital X of x and capital Y of y, and how we may get signs in one of these variables and exponentials in the other, or vice versa, or there is this in between case when if the separation constant turns out to be 0, then you can get sort of linear solutions in each of x and y. Now, which of these do we want for a particular scenario will depend on the boundary conditions. So there are these two important boundary conditions which are the standard sort of starting points to apply the separation of variables technique. And so one of them is called the Dirichlet boundary condition. So the Dirichlet problem for a rectangle is where we specify the value of the function at all points on the boundary, right? So you have a rectangular curve, and so we are interested in finding, for example, if you are interested in finding the potential, electrostatic potential inside a rectangular region, and we are given the value of the potential at every point on the boundary, right? So and then our job would be to solve for the Laplace equation within the rectangle and ensuring that u phi of x comma y, right, will take the particular values which have been specified on the boundary. Now, even within this very specific way of specifying the boundary conditions, it's convenient to actually set three of these to be 0 and come up with a function for one of these sides, right? So suppose we have in the general problem is, of course, you will have different functions describing the values on each of these four boundaries. So we can actually think of this as a scenario where you add four different problems. So all of these are sort of linear problems. Therefore, you can take solutions for one of them, take a solution for another problem, a third one, a fourth one, and so on, and just simply add them, stitch them together. Literally, you can add the solution in this case, where in one problem you take some three different sides to be 0, but the fourth one is non-zero. You put the value of the potential at that point, and you consider another situation where you put a 0 in that one, but take some function for another side, and then a third one where you put in the function corresponding to the third side alone, and a fourth one where you put in a function corresponding to that side alone, whereas you keep the others 0. And then using the method that we're going to describe here, you can separately work out the solution for each of these and just simply add them all up, and that will be the solution for the overall problem with the full boundary conditions. So it is for that reason that it's enough to study this particular case. So the particular case I'm considering is to have this rectangle which is two of whose sides are the y-axis and the x-axis, but also there is a boundary which is set at x is equal to a, x is equal to a, and y is equal to b, right? So it turns out that at y equal to b, the value of this u function u is taken to be 0, and on the line y is equal to x is equal to a, also u of a comma y is 0, u of 0 comma y, that is along the y axis, is also 0. It's only along the x axis right at the bottom that and the value of this function is chosen to be some f of x. I mean, if this were also 0, then of course the solution would be completely trivial. It's 0 everywhere, right? So some non-trivial function f of x is assumed for the bottom boundary. So we will see how to solve for this using the general solution that we had. So one observation we make is that there are these, out of the 3 different cases of solutions possible, actually 2 of them are not applicable here. So this is something that we can sort of read off, right? One is, suppose we try to look for a solution of this linear type, ax plus b times cy plus d, right? So if you try to put, when x equal to 0, so suppose I put x equal to 0 and y, so I'll have b into cy plus d must be 0, and so that will imply either b is 0 or cy plus d is 0. Cy plus d cannot be 0 because y takes various different values. And similarly the other conditions, you can check this. Each of the conditions, if you put in, basically you will end up with a scenario where all a, b, c and d have to be 0. So you get only a trivial solution. And likewise for the boundary conditions which are given here, if you take exponentials along the x direction and sinusoids along the y, it's not going to work out, right? So if you have to choose e to the px, you have to choose some solution like c1 times e to the px plus c2 times e to the minus px, the whole thing multiplied by c3 times sine of py plus c4 times cosine of py. Suppose you make an ansatz like this, or it's not really an ansatz, it's suppose you choose this to be a solution. Can you fix these c1, c2, c3 and c4 such that these boundary conditions will hold, right? So if you put x equal to 0 and leave y as it is, it has to go to 0. And again, if you put x equal to a and leave y as it is, again it has to go to 0. So you can convince yourself that it's not going to be possible to use exponentials and also satisfy 0 above and a non-trivial function at the bottom, right? So this is something that I will allow you to play with and convince yourself. It's just maybe a few lines of algebra, right, to see for yourself. But basically the idea is that you try to plug in this c1, c2, put x equal to 0 and y, leave it as it is, x equal to a, leave y as it is, and ask what conditions will it yield on c1 and c2 and c3 and c4. Put in all these 4 conditions and you will see that you will end up with c1 equal to 0, c2 equal to 0, c3 equal to 0, c4 equal to 0. So the only way you can satisfy these boundary conditions for, if you assume this set of solutions, is if you get a trivial solution, which is not really useful, right? So we want a non-trivial solution. After all, I mean, you also have to satisfy this, u of x comma 0 equal to some function. So the only option that can also do that and satisfy these other boundary conditions in a non-trivial way is if you choose the other possibility. If you take the sinusoids along x, right, I mean, you can set them up in such a way that it goes to 0 here and it goes to 0 here, and then the exponentials can be chosen in such a way that at the bottom part you get a non-zero value, but only at one end you have to make it go to 0, right? So you can set up these coefficients. You have to take linear combinations of the exponentials, so at one end you can take it to 0, but you cannot take it to 0 at both ends. Whereas with sinusoids and cosines, we know that sinusoids are functions which they repeatedly go back to 0. So you can choose your the other end. You fix one end to be 0, and then you have to choose your other end to be such that it's at one of the other zeros of sin pi. So you'll in fact get infinitely many possibilities, right? So which is not the case if you choose exponential. So basically the idea is that given the boundary conditions, you must work out whether it's sinusoids which are going to be the right kind, or if it's which direction do you want sinusoids and in which direction do you want exponentials, right? So this is the first thing to work out. Once we have this, then we will see what restrictions on this P are going to be brought in by the boundary conditions, right? So P, of course, at this point can be any real number, right? So we will take now we will take this to be our solution and see if we can fit it to these boundary conditions, right? So let's start with the fact that u of 0 comma y, right? So this is the third condition, u of 0 comma y must be equal to 0, right? So I mean, this has nothing to do with y, it's all about x. So if I put x equal to 0, then this must go to 0. So we cannot have any of these cosine functions, because cosine functions will give you some stuff times y which will remain, but we don't want that. So no matter what y is, if you put x equal to 0, it must go to 0. So we are left with only sinusoidal functions. So in order to ensure u of a comma y equal to 0, so this is like what I was saying some time ago, which is that if you want your function to go to 0 on opposite ends, you must take sinusoids or cosines in that direction, and if you want your function to go to 0 on only one end but remain non-zero at the other end, then exponentials are appropriate, right? So now you see that in order to ensure that u of a comma y equal to 0, we must choose P such that you get back a 0 of this sinusoid. So and that means sine of PA must be equal to 0. So P must be some n times pi by a, right? So PA must be equal to some n pi, so which is the same as saying P should be some integral multiple of pi by a, right? N equal to 0 is trivial, so we'll start with n equal to 1, n equal to 1, 2, 3, so on. Therefore the solution we seek is going to be of this form: u of x comma y is going to be in general a summation over n running from 1 all the way up to infinity, sine of n pi x by a. So already we have got a restriction on what P can be, so it's going to be n pi by a times x. Then we have these two different possibilities. We have both this positive exponential and exponential of a negative p times y. Both of these we have to keep track of. So there are these coefficients that will have some index n, alpha n and beta n, e to the n pi by y by a plus beta n times e to the minus n pi y by a. So now we must use the other two boundary conditions to work out these coefficients. Now one of these conditions is going to actually connect these alpha n and beta n. So if you take the boundary condition u of x comma b equal to 0, so which is this first condition, u of x comma b equal to 0, then we see so if you put y equal to b, so then we have alpha n times e to the n times pi b by a plus beta n times e to the minus n pi b by a, right? So this has to be 0 for any value of x. So this is not going to count at all. So each of these factors must go to 0, and therefore immediately it tells us that beta n is related to alpha n in this manner. So beta n is equal to minus alpha n times e to the n pi b by a, the whole thing divided by e to the minus n pi b by a. So u of x comma y is equal to summation over n going from 1 to infinity alpha n sine of n pi x by a times, you can actually pull out this alpha n, because beta n is also really alpha n times this stuff. So then you can write this as e to the n pi y by a plus, well, it's a minus e to the minus n pi y by a, the whole thing divided by e to the minus n pi b by a. Now that you can rewrite this, bringing it to the numerator as well in this manner, and then you can pull out this alpha n, and therefore if you multiply both numerator and denominator by 2, and so you have 2 alpha n divided by e to the minus n pi b by a, sine of n pi x by a, you leave it as it is, and then we have exponential of this stuff minus exponential of negative of the same stuff divided by 2. That's nothing but hyperbolic sine of n pi times y minus b, the whole thing divided by a. So now we have put in 3 of these boundary conditions, so we just need to put in the final boundary conditions, which is a whole function, and that's why there is a whole set of coefficients n equal to 1 to infinity, which are still unknown to us, and all of that is contained in this function f of x, which we can extract now. So the condition u of x comma 0 equal to f of x is the same as saying, f of x must be equal to this summation n equal to 1 to infinity 2 times alpha n divided by e to the minus n pi b by a times, now this hyperbolic sign, y is 0 here. So we have n pi minus n pi b divided by a times sine of n pi x by a. So this is actually nothing but a Fourier series representation of this function f of x, right? So f of x is defined in this interval from 0 to a, right? So f of x is defined in the interval x will go from 0 to a, right? So, and therefore it is being written in terms of signs, right? So there, if you are given just a function from 0 to a, it can be expressed in terms of sines or cosines. So this is really a Fourier series expansion of a function who's defined in the interval from 0 to a. So the way to think of this is to continue it to the interval from 0 to minus a. If you take it to be an even function, then you will be able to express it in terms of cosines, but if you take it to be an odd function, you'll be able to express it in terms of sines. But in the end, if you're going to care only about the particular interval that you're interested in, it doesn't matter, right? So you can do either of these. Now f of x is here, basically we already see that this is nothing but a representation of this function f of x in the interval 0 to a in terms of sines. So this is nothing but a Fourier series expansion, for which if you had been asked to work out this expansion for the function f of x, so the way to do this is, to think of this entire thing as the coefficient corresponding to sine of that particular frequency, and so we know that the way to solve for this is to multiply throughout with just sine of n pi x by a, and then integrate from 0 to a. All of these terms except one of them that we are interested in will just vanish, right? And then you will get the particular coefficient that we are after. So, and that we can simply write this particular coefficient as 2 by a times integral from 0 to a f of x times sine of n pi x by a dx, right? So this is nothing but an expansion. This is the trick we're using, which you work out Fourier coefficients. So now we are almost done. So we just basically managed to work out the final solution. Now u of x comma y is nothing but summation over n going from 1 to infinity an times sine of n pi x by a times hyperbolic sine of n pi times y minus b divided by a, where these coefficients an are given by this whole stuff, right? So this capital An is actually nothing but this small 2 times alpha n. So yeah, you have to be careful about this factor, and so in fact An is given by just 1 divided by hyperbolic sine of minus n pi b by a times 2 by a times this integral 0 to a f of x sine of n pi x by a dx, right? So this whole stuff, so let's see. So we have this expansion. I mean, this is the expansion that we are after, and then we came to here, and then we managed to equate these coefficients, and then basically we managed to show that the new coefficient, the final coefficients an are simply written in terms of this expansion, right? So you should just go over this and convince yourself that indeed you got all the factors right. But basically the idea is, it's a combination of bringing in all the boundary conditions in a systematic way. First of all, choosing the right kind of solutions, and then also making sure that we extract the right kind of Fourier series. So in this case, it's a sine Fourier series, and then get the coefficients out. So let's look at the other kind of boundary conditions, where I have an example where the other kind of Fourier series also comes in. So that's related to this Neumann problem. So the Neumann problem for a rectangle specifies not the values of the function on the boundary, but the derivative of the function at all the boundary points, or in some sense the gradient of this function, right? So it's, suppose we look at the same kind of a problem, but we specify dou u by dou x on for all values of for when x equal to 0 and for all values of y, right? So to be 0, that is dou u by dou x, it's a rectangular problem again, and then dou u by dou x again at the other end, a comma y is also taken to be 0. But if you're going in the vertical direction, it is dou u by dou y that is specified. So that is when x for all x but y equal to 0 is also 0. So in along the x-axis, so we have this rectangle along the x-axis, dou u by dou y is taken to be 0. It's only in this stretch dou u by dou y along for all x but at y equal to b is taken to be some function f of x. So this would be a a Neumann problem. So once again, this is something that you can check explicitly, is the other two cases of solutions do not contribute here, right? So you can play with this, you can shift the boundary and then you will see that some other kind of solution will become relevant, right? So basically the idea is that you must see on what opposites ends are desire for zeros to appear, and there will be two other ends, one of which will be 0 and the other one will be non-zero, right? So depending upon that, you have to pick the right kind of solutions. Again, this linear solution times linear solution is not going to work out. You'll simply get the trivial solution a equal to 0, b equal to 0, c equal to 0, and d equal to 0. And if you choose exponentials along x and sines and cosines along y, you'll see that for the Neumann problem, it is the derivative which needs to go at at these two ends. So this is again going to fail. And but on the other hand, if you choose the other condition, which is if you choose sines and cosines along the x direction and exponentials along the y direction, you can set up the derivatives in such a way that one end will go to 0 in the y direction, that is at the bottom end, and at the top end it's going to be this function f of x, right? So that's what we will look at now in some detail. So if you have dou u by dou x at for x equal to 0 and for all values of y to be 0, now the only way that can happen is if sine functions don't appear, because it's about the derivative, right? If the sine functions appear, then if you take the derivative, you will have cos functions, and if you put x equal to 0, you will get a non-zero value. But here, if you take the cosine functions, take the derivative and put x equal to 0, that's indeed going to go to 0. And on the other hand, if you want to ensure dou u by dou x of a comma y to go to 0, then we must choose our p in such a way that sine of pa equal to 0, right? So if you take cosine of px, take the derivative, then you will get sines of pa's, and then if you manage to choose your p in such a way that sine of p equal to 0, which happens when p equal to n times pi by a, n equal. So now 0 is also important because it's about the derivative. So you start with the cosine function, so that's going to give you a constant, so as we will see. So we start with n equal to 0, 1, 2, 3, so on. Therefore the solution we seek is going to be of this form: summation over n equal to 0 to infinity cosine of n pi x by a. So if you put n equal to 0 here, you have a 1, right? So you have alpha n times e to the n pi y by a plus beta n times e to the minus n pi y by a, right? So you can take this on sorts and quickly convince yourself that these two conditions hold. This one and this one automatically is taken care of if we choose this solution, right? So two of these conditions are already done. In order to do the other two conditions, there is one condition which is quite straightforward, right? So we have chosen the other end here to be to go to 0. So it's actually an easier problem than the previous one, in the sense that the relationship between alpha n and beta n turns out to be simpler here. So if you choose dou u by dou y of x comma 0 is equal to 0, you can quickly check that if you take the derivative of this function basically and dou u by dou y, so that's going to give you this stuff n pi by a, then this stuff with a minus n pi by a, and then you have to put y equal to 0. So immediately you'll see that you'll get beta n must be equal to alpha n. So we have this simple form for for our solution, it still needs to be completed because we have to put in the other boundary condition. But here I have managed to multiply and divide by 2 and then rewrite this sum of these exponentials, and then I have a divided by 2. I can rewrite it as hyperbolic cosine of n pi y by a. So I have 2 times alpha n times cosine of n pi x by a times hyperbolic cosine of n pi y by a. Finally, we have this boundary condition for the fourth side, which is dou u by dou y of x comma b is equal to f of x. So if I plug this condition also in, now I have this Fourier series representation for f of x, but in terms of cosines now, right? So this, whether you get a cosine series representation or a sine series representation, will depend on the boundary conditions involved. So basically the idea is that your function f of x is defined in the interval 0 to a. So there is a way to describe this function in terms of cosines or sines, because you can extend it to be an even function or you can extend it to be an odd function and then extract this Fourier series, and it doesn't matter as far as you're looking at only the interval 0 to a is concerned, both are completely legitimate solutions. So in this case it's a Fourier series in cosine functions, and so therefore we have this n pi by a also, which has come in because we have to take this derivative, right? So when you do dou u by dou y, so this n pi by a comes out, and then cosh becomes hyperbolic sine. You have to check all of this. It's just some elementary calculation involved, and then finally we simply recognize all this stuff times this stuff as really like the coefficients of this cosine series. So all this stuff, which is really the coefficient, is nothing but 2 by a times integral 0 to a f of x times cosine of n pi x divided by a dx, right? So this is the theory of Fourier series representation, right? So you can multiply throughout with this function and convince yourself that indeed if you have cosine squared, that's going to give you a non-zero value, and specifically it's going to give you this normalization. But these are in some sense orthogonal functions, right? So if you multiply two cosines with different frequencies and then integrate from 0 to a, those are all such terms that will vanish, and so finally the problem can be written, the final solution can be written as u of x comma y summation actually this n needs to go from 0 to infinity, so it will go from 0 to infinity an cosine of n pi x by a hyperbolic cosine of n pi y by a, and you can convince yourself that indeed an is nothing but 2 divided by n pi times 1 over hyperbolic sine of n pi b by a times integral 0 to a f of x times cosine of n pi x by a dx. Okay, that's all for this lecture. Thank you.